So the dual stage with a current mirror, I now called it a current mirror instead of a inverting current amplifier, and we are they have the idea to make it with PMOS. You can also put NMOS there, but I was thinking already a little bit about biasing. I think, well, I'm going to make it with PMOS, and then selected the transistors such that I have let's say still decent inversion coefficient, but a much lower GM than the first transistor, than the first transistor, the input CS stage. The much lower GM then would give us indeed a very low contribution of the noise to the equivalent to the total source reverse noise, which means that we can still obtain the specifications. So here I do it by making the transistor 500 micrometers wide and a length of 500 nanometer, and having the same operating current as the first transistor, the first stage, both both transistors. And you see, the nice thing about SlideCap is you don't have to worry about the implementation of the biasing. It's something I simply don't want at this stage, because any effort I put in biasing of something that is not feasible at the end is lost effort. I first want to have a signal path that is feasible, and if the signal path is feasible, if I can achieve the bandwidth, if the circuit is stable, if I can use if the frequency compensation can be applied so that it is stable under all conditions, then we have a reason to go for the next step in the biasing. You must realize yourself that the further we go in a design process, the more details we have to deal with. So you first want to have the main points set in the right place, the main characteristic, the noise performance, the bandwidth, and of course not in 3 digits, no, but in a factor 2 or 1.5 or whatever. So you have enough room for adding errors at a later stage. But the further we go, the more detailed design activities are required, the more work is required, the more time is required for simulation. And so you only want to shift this do it at the end if the thing is feasible. So at this stage, we are focusing on feasibility, on rough numbers, indications. Is it a good solution, or can another solution really be a lot better than this? That is what we are how we are building up the design, doing structured electronic design. And that's why we need SlideCap. Because now, for example, you could even sweep the operating current of the output stage and see what it does with the pulse zero pattern. Can you imagine how you would need to do that in LT-SPICE? You cannot plot pulse zeros. You have to read it from both the plots. Um, but sweeping an operating current is not as simple, because all the biasing should be adapted to do so. Here, it's just a parameter, and the small signal parameters of the transistors are quite accurately related to the geometry parameters and the operating conditions. That is why we are going to do the small signal design completely with SlideCap, and that's why you have to put effort in making the models. So on device level, you have to be sure that the models are good enough, are matching with the models that are in LT-SPICE or in Cadence. So the dual stage mirror, there's also a file, and I will demonstrate this file as well, of course. And we have low transconductance PMOS, and we will study the influence on their bandwidth. That is what we want to see. And extra attention now we are going to pay to the selection of the loop gain reference. Where do we select the reference, the loop gain reference? Every transistor that is there has a local loop because of the feedback capacitance, the internal feedback capacitance, or the Miller capacitance, whatever you call it, but basically the gate drain capacitance. So everywhere where you put where you want to select your control source of the stage as reference, you are in a local loop. This will be clear in the asymptotic gain. And you can break the local loop, and that is a nice thing also about SlideCap, just by putting the capacitance to 0. Now you would say, maybe, are we just going to put the capacitor to 0 and then the whole circuit changes? Well, now remember, In most cases, if we do a correct design, then the feedback capacitance says something about the sum of the poles, but not about the product, because it's much smaller than other capacitors. Look, for example, at the first transistor. We have, maybe you can imagine the small signal diagram under it. You have CGS, but the stage is driving 2 CGS of P transistors. And those P transistors are also quite large. So there's a capacitive load on this circuit that is much more, a much larger capacitance than probably the feedback capacitance of this stage. And you can verify this later on in the parameters given by slide cap. And here, of course, the stage is almost shorted because we have basically 1 over GM of the stage, but GM is much smaller than of the first stage, so we still may have some voltage gain. But the Miller effect will be really low, also because of the high capacitive load. So what we could do is just remove the capacitor from the first transistor, take our loop gain reference there, and then replace it, but then only studying the gain and studying the change in the gain by placing it or leaving it out. If there's no significant change, then the feedback capacitance doesn't play a role. Then there's almost no Miller effect in the stage. And that's what I want to demonstrate as well for this design.